everyone. Welcome to the 60-inch telescope here at Mount Wilson. My name is Dr. Jenny Krestow. I am one of the astronomers at Glendale Community College here in Southern California. And this is one of our virtual star parties. I think this is the 5th virtual star party. We have had live streaming from Mount Wilson this winter, although it's now spring 2021. I am joined this evening by 3 other astronomers. My husband, Dr. Chris Burns, behind us, who's an astronomer at Carnegie Observatories. Mr. Tom Meneghini, who is over here behind me, who is the executive director here at Mount Wilson, and Mr. Richard Bell, who is our telescope operator tonight, who is over by the telescope. So I'm really pleased that you guys could be joining us this evening. We have some sites set up, or some targets that we are hoping to be able to observe tonight. However, the conditions here are not ideal. It is pretty windy, and the seeing is not the best it's ever been. But we're going to start our evening by having a look at the moon. So let us head over to the attic view. And the attic camera is actually attached to the 60-inch telescope. And this is the view of the moon using the historic 60-inch telescope up here at Mount Wilson. So the attic camera is a special camera. It's not quite like the cameras you would have on your cell phone. It is a camera that fits very neatly, and it's made specifically to fit into the slot where an eyepiece usually goes on a telescope. So if you've ever used a telescope before, you know that you probably just put your eye right up to the telescope, and you can have a look through the eyepiece and see the moon or planets or other wonders of the universe. This telescope is specially designed to be used with telescopes. This camera is specially designed to be used with telescopes, and it is giving us a pretty close-up view of the moon. Now, one thing you will notice about this image is that the moon kind of looks like it's underwater. Right now it seems to be shifting around, and that is because we are looking through the Earth's atmosphere at the moon. And just like, a rock or a penny on the bottom of a pool will look like it's dancing around if the water that fills the pool between you and that penny at the bottom causes the image of the penny to shift around. The atmosphere of the Earth does pretty much the same thing. So how much the atmosphere causes what we're looking at to shift around is measured by, or it's, described by by something called atmospheric seeing. That's what astronomers call it. And right now, you can see that the atmospheric seeing is substantial. We have pretty poor seeing, as the phrase goes. We have a lot of shifting around. We've got things that are not quite steady. On a really good night here in Southern California, we can have a really crisp, clear, still image. We are not getting that tonight. So we are seeing a moon that looks like it's having a dance, which is okay. What we're looking at the moon, or on the moon, is some craters. And there are, you can see kind of toward the bottom at the very center of the image, there are craters within other craters. And there's also, it looks like, a ridge or a mountain range that kind of goes from left to right, upwards a bit to the right in the top part of the image. But these are all geological features on the moon itself. So the moon, contrary to popular stories, is not made of cheese. It is made of rock all the way through. And what you're looking at are features on the rocky surface of the moon. Not sure which part of the moon we're actually looking at. The image we get from the 60-inch telescope is very, very zoomed in.
So this, that really neat one there, you can point out that has the
Okay.
craters inside the craters.
I'm not sure if I can do that with my mouse, but the center crater,
Oh, I'll do it.
crater within, oh, well.
That's right.
So Chris is over on the other monitor. So this part there, which is craters within craters,
is this one here. And that is called
it's within Mare Imbrium,
Cassini.
and it is called the Cassini Crater, named after Giovanni Cassini, who was an astronomer that lived in the 1600s. How do I know this? Because the Cassini spacecraft was named after him, and the Cassini gap in the rings of Saturn also named after him. So Cassini, unless this is a different Cassini, Cassini is a very famous astronomer, and this crater was named in his honor. This crater within, actually I think it's a couple craters within a crater, within a mare, was named in his honor. Now a mare, for those of you who may not know, is what Galileo believed was a sea or an ocean. Mare is Latin for sea. And when Galileo looked at the moon, he saw these dark, very smooth areas. And his telescope wasn't the best, so he couldn't really tell what the material was. We now know it's rock. But for him, it was very smooth, and he lived in Italy, not far from the ocean. So he thought that this could be an ocean on the moon. And they didn't know what the moon was like, but it was not out of the realm of possibility, according to the scientists in the early 1600s, that the moon could be somewhat similar to the Earth, in that it could have some vegetation on it, although that wasn't apparent, and it could have these oceans. So the name Mare stuck, but we realize now that these flat, darker areas aren't in fact filled with water. They are ancient lava floodplains that formed billions of years ago when large asteroids slammed into the moon and cracked the thin crust that had formed over the molten ball that was the very young moon. So the magma would have flowed up through the cracks in the bottom of the craters that these asteroids would have formed, and then flooded the bottom of these craters and cooled, solidified, and became the mare that we see today. But the mare are very old, so there are more recent impacting events that have created the craters that we see kind of on top of these ancient lava flows. Oh, I'm just being pointed out some information about the Cassini crater that we're looking at here. So I think Chris still has his cursor kind of circling the Cassini crater. There it is. That crater is 57 kilometers across, so that's about 40 miles across. And it says Giovanni Domenico. It must be Giovanni Domenico Cassini. Was an Italian-French astronomer who lived from 1625 to 1712. And it is a circular depression, usually impact-related, but these craters can sometimes be volcanic in origin. So this is our view of the moon.
The next one over to the right is called, oops, this one here.
Okay, so the big one off to the right or to the left?
To the right.
To the right?
Backwards.
Aristyllus. That's the one that is kind of in the shadow just off the screen over to the right-hand side with a very kind of gentle peak in the center. Aristyllus.
Greek astronomer, 280 BC.
The one, yeah, that one off to the right.
So
Is a Greek astronomer?
that's what it said. It just said
Well,
Greek astronomer.
BC is what I heard.
So,
BCE.
Let's search for
So Apollo 11 did land in.
It's close to here.
Well, they landed in Mare Tricolatatus, and this
Yeah.
is Mare Imbrium.
Well, okay, when I say
Okay.
close, I mean
Close.
relatively speaking.
We have many monitors going on here, and
Want to show the outside view?
the outside view,
The
the dome
telescope
view.
view.
Yeah, why don't you do that?
Okay.
Give us a dome view of the telescope, or a dome view of the telescope. A kind of wide-angle view of the setup that we've got going here and the telescope itself, and maybe even a shot of the moon through our.
Want to do the wide one, or do you want me to do the?
Just do the mobile one.
Okay.
Okay.
You can. Okay, so hopefully this doesn't cause feedback. We have a lot of audio devices tonight, and so sometimes we forget to turn one on and turn one off. So this is the 60-inch telescope, and I'm going to pan up, and we should be able to see what the telescope is looking at through the dome. And it's good and bright, so we can actually see it with my iPhone. And so you can tell that the telescope is pointed straight at the moon, and it's looking through that rectangular opening in the dome. We call that the shutter. And we just have to make sure that the shutter is pointing in the same direction as the telescope. Otherwise, you don't see very much. And coming back down, the bottom here, all these cool things are counterweights. And they just make sure that as the telescope moves around the sky, it remains balanced. And hidden underneath there is our mirror. If we've got a white light, which I think I have in my pocket, we can have a look at the underneath real quick. Da-da-da. Okay, so coming under here, hopefully what you can see down in there is green. And that's because we are looking at the bottom of a circular piece of glass, 60 inches across, and about 7 inches in width. And when you have that much glass, you get this sort of green color. Anyone who's got a fish tank, if you look at the fish tank glass on the side, you sort of has this nice green color. It also kind of looks like there's something in the glass, like these little discs and things like that. But what you're seeing is actually a reflection of the mirror supports through the glass. So here, that's the real mirror support. And then if you look up into the glass, you'll see like a green version reflected back at you. And so on the top surface of this glass mirror, we have a coating of aluminum, and that reflects light in both directions. So you can see the underneath as well. Great. Mirror itself weighs almost a ton, just shy of a ton. And the whole telescope itself, the mount and the cage and the secondary mirror up there and this big wheel on which it rotates, all of that comes out to about 22 tons. And that's a lot of weight to put on a bearing. And so what they did in this case was they have it floating in a bath of mercury. So this big sort of cylindrical tank here that you see has about 600 pounds of mercury in it. And that's enough to have this entire telescope, this entire 22 tons of steel and glass float in it. And it's a very nice low friction way of taking the weight off of most of the bearings that take a little bit of the weight that remains. And the whole thing is nicely balanced so it can rotate left, right, and pivot up and down. And as we go to different objects tonight, we'll show you what that looks like when we move the telescope around. And the last thing I'm going to show you before we go back to the other view is this is our camera right there. And let's see, where's the label? It's probably on top. Oh well, this is called the Attic Horizon 2. And as Jenny said, this is a CMOS camera. And a CMOS camera is very similar to a CCD camera that you would have on your phone. The big difference is that CMOS cameras can be read out a lot faster than a CCD. And so it gives us a more kind of real-time view of what's going on in the telescope. And that is connected to a PC, which is on the side of the telescope. And then that comes back to our computers. And that shows us what we're seeing through the telescope. And normally, under usual operating conditions, we'd have a group up here, and instead of a camera, we'd have a big eyepiece sitting there, and you would walk up and down this ladder to go up and have a look through the telescope. But instead, we're going to do this remotely until the COVID pandemic is over. How's that? Good enough?
That's awesome.
All right. So bring this back down here. Yeah.
Head back to the view, the attic, and then back with our regular microphone.
So now we should show folks the other. Can we have a view of the telescope? The webcam view of the telescope? Just so we can show people what we're
So that was the 60-inch telescope that we are using to show you this image of the moon. But coming online now is another telescope that is part of the Mount Wilson, I guess family, part of the Mount Wilson Observatory complex. It is a smaller one, an 8-inch?
130 millimeter, yeah.
130 millimeter, which is a 5-inch refractor. And
this here.
yeah, Chris is circling with the mouse the actual telescope. Well, the telescope is that bit there, and then the white cylinder is the mount that the telescope is mounted on. One thing about telescope mounts, as my students are finding out because they are making their own telescope, you really need something stable. If it is wiggling around, if you're holding a telescope up with your arms, you will get very tired arms very quickly, and what you're looking at is going to wobble around more so than what I was just showing you of the moon. So you need a very stable mount, and these are often made of steel or concrete. By the way, what was going on in the background there? Can you just bring it back for a second?
Sure.
All of that white stuff, that is actually LA, the lights of LA below Mount Wilson. I'm not sure which part of greater LA that is. Monrovia, Arcadia, that kind of neighborhood, because it's looking a little bit southeast of Mount Wilson itself.
So we're going to bring over the view through that telescope.
But coming up now, is the view through the 5-inch refractor. So you can see this is a really kind of zoomed out view of the moon. It is beautiful. You can still see the moon kind of dancing around. And where was the crater that we were looking at earlier?
Right here.
Yeah, so you can see how we're really zoomed in with a 60-inch telescope, and with this refractor, we've got a nice wide, kind of a wide-angle view. And I'm not sure what Chris is doing, just looking around at different parts.
I mean, here, if we see the full, I think we can do auto, and then it shows the whole.
Oh, yeah.
The whole view.
That's the whole view of the moon that we can see tonight. The moon is not full tonight. It is a waxing gibbous moon. I believe it's 9.8 days old, or days since the new moon. And I can see it almost directly above my head. So it's pretty much at the zenith point in the sky, but it is quite bright. It's reflecting a lot of sunlight back in our direction. And a lot of people think that the rock that the moon is made of is kind of a very light gray. Well, that's deceiving because it's actually quite dark gray. But it just reflects so much sunlight back to us that it just looks very bright, and we perceive that kind of as white rock. Very bright, especially against the dark sky that usually surrounds it. So this is what we have of the moon.
Yeah, okay.
Any good stories? Lunar stories that you guys know of?
Stories.
Like the man in the
I
moon?
was hoping to go try and find the Apollo 11 site.
I can tell you roughly where it is if you
We can't see the
zoom.
impact or L-cross location at the South Pole. It's not visible.
No.
It's in the dark
Let's
area.
do 125? No,
Oh.
sorry, no, 175 maybe. So, if I remember correctly, it's in here somewhere, isn't it?
Apollo 11? No, go up.
No?
It's
Up.
Mare Tranquillitatis, which is the man in the moon, which is the other way round. You can't shift this round, but so I think the darker of the two.
Oh wait, it's over here, isn't it?
Yeah,
That's
yeah.
the way. Okay.
That's down there.
So we are currently there, so if we go north, then we can try.
We are gonna try and look for the Apollo 11 landing site. We will not see what is left of the lander because there was some instrumentation left. We won't be able to see that, but we may be able to see where it landed.
Just jump over here. Hey, Michael. Hey, Michael. Oh, it's Michael Rudy?
Michael Rudy just said hello. You're getting some love there, Michael. Wow, this is a very golden view of the moon.
Yeah, I'm not sure why the white balance is.
Yeah, our white balance is a little off tonight. And one of the things with trying to navigate around when we are looking at the moon is that if you press to go left, the image shifts right, and if you press to go up, the image shifts down. It's kind of hard to figure out which way you're going because telescopes will invert and flip the image often. So we also, there's a delay between when you press the button and then release the button for motion and when the telescope actually moves. I should use the technical terms for this. This is called slewing the telescope.
Okay, so this is one of them are at the top. I think I need to go.
Let me see if I can get so one of them are at the top, Chris says. Let me see if I can get a lovely big picture of the moon. Yes, that is going to be Mare Crisium. Seriously, there's a crater called Picard. I kid you not. So we have an app called Stellarium, and mind you, it's a small crater. It is called Picard. It's the one that is most centrally located in Mare Crisium. And then I want information about it, but it's not giving me any information. Like how big it would be or anything. Oh, it's a double ring crater. That's beautiful.
I think this is close to the center.
Is it?
I think so. 'Cause it's like a little finger that points out. But it's hard to say because
Focus is on.
It is. trying to find that on this
On the, let me grab the other thing.
moon.
It's over here.
Yeah, isn't that your, right there?
Yeah, right there. I think that's,
There's your little ring.
yeah. So, does it have the site on there? I did a search for it.
Did you?
Yeah.
Hang on, let me
just
do
go
another.
to search.
And then
Yep.
Apollo 11.
Just hit the search. Okay, and then, yeah, feature on the moon. Okay, and then center, lower left.
Center.
Oh,
Ooh,
nuts.
we're a little,
We're a little off.
off.
So it's,
Yeah, you're down there in Mare Serenitatis. We need Mare Tranquillitatis.
so we're on that, I guess?
You're down here, and you need to
Okay.
come over here.
Can you tell us which way that is?
Oh, that is difficult.
So we are,
Demanding you are.
where are we? Oh, we are
Oh,
here?
right there. See this right here? This little loop,
Yeah,
little loop.
okay.
I think you're down. Are you over here or down here?
We're right in here.
Okay.
I think we're
So-
up here. Oh,
Yeah, that's where we're at. We're right there.
okay, so we gotta be, oh, we lost it.
Are you up here or
Yeah.
down here?
Well, this is 90 degrees
Remember,
off,
it's flipped.
Oh, right.
or flipped, yeah. Okay,
We're
so
down there.
we wanna go, except I don't know which way that is. Just do this. None. So we're up here,
Mm-hmm.
so I guess we wanna go south? Assuming that that's correct.
Okay. So we want to
South
go.
sounds good.
Looks like we want to
This
go
is
right
like-
to there,
The hunt for Apollo 11.
Yeah, so,
right there.
okay, assuming that that's south, which, I
It
don't
would
know.
have to be because
Okay,
Dun dun
there's no,
dun.
there is no south. We can't see the south pole.
I guess I meant south in the sky.
I knew what you were talking about, Chris.
Okay. You want to try
South,
going
south in our version.
south, please? Let's see if that
South
takes us-
according to the direction the telescope is
that
going
takes
to
us where we
slew.
wanna go. Okay, that's taking us that way. All right. And now can we go west?
So Michael is commenting on the cheddar cheese moon configuration this evening. It does look a bit like cheddar
East.
cheese.
East.
The last moon direction.
Oh, that's that up there.
Remember, our camera was turned 90 degrees, which is weird.
Through there. Now we're in the
That's a
gap.
very bright
And
one.
that's that. Okay, hold on. So where is it relative to that? So
To-
it's right in that little dip there, right? Little- just to a little bit of that.
Just to the left of the dip.
Okay. All right. Well, we're there. That's it.
That's it. That's
right.
very exciting.
So for some reason,
Wow,
the
that is
color
really
balance
exciting, actually.
is,
I've never seen a really zoomed in version of where Apollo 11 landed. Now, you can zoom in all you like with our telescope, and it will not, unfortunately, give you any image of what was left behind from that historic moon landing, because at a distance of approximately 380,000 kilometers, 234,000 miles, we are not seeing something the size of a car. It is just too far away, and our telescope does not have that type of resolution.
all right.
There
So-
have been images taken of the landing sites, the Apollo landing sites, by the LRO, the Lunar Reconnaissance Orbiter, but that is a spacecraft that is orbiting the moon at several hundred kilometers above the surface of the moon, not at a distance of 380,000 kilometers away.
All right. I think I put the mouse right about where.
Hang on, let's go back to search, Apollo 11.
For those of you at home, we're using Sky Safari.
And Sky Safari is not working too well. Possibly.
And luckily, Sky Safari is not supporting this video. So we just
Why is it not? I'm double click. Come on.
just hit return.
Select.
Hit return.
Hit return.
There you go.
There we go.
Center. Oh, okay. So it's more out, kind of here, I guess, right around.
Yeah,
Yeah, right around. there.
that's about perfect. That's where Apollo 11 landed. Almost, no more than almost 52 years ago. It was July 1969.
Yep.
So we're gonna have the 52-year anniversary coming up. That's pretty amazing. I mean, I know a lot of young people these days are like, oh, what good stuff did they do in the 60s, man? They were smoking too much then. Well,
That's right. We did have Buzz Aldrin in this
in
dome.
this telescope dome? Wow.
Yep.
Buzz Aldrin was here. I feel privileged to be standing in the same spot.
And we'll bring over the other view of the moon just to show a zoomed out sense where that is. So it's right over here. Is that cool? Yeah.
What's that?
So just showing the refractor view, just to show where it is in the Sea of Tranquility, which I'm guessing is this bit here. Yeah. All right. So there we go. All right. So that was the moon. I think we've done the moon.
We've done the moon?
Does anybody have questions about the moon?
Questions about the moon. Hello from PCC. Hey, Jake. I'm so glad you could join us. This is our Mount Wilson party.
Nice.
Oh, I am looking at a picture of Tom Meneghini, our executive director who's with us tonight, and Buzz Aldrin wearing an Aldrin t-shirt.
Yep.
Yes, just so everyone knows who it
Just so
is.
you
It's
know
like
who
a
he is.
giant name tag here in the dome. A number of years ago now, because he's passed.
About
Yeah.
3 years ago?
3 years, yeah.
He's in the 100-inch.
Yeah, well, not in this dome, in the 100-inch dome then. But this is our view of the moon. Are we going to move on to something else, gentlemen?
I think it's about time to move on to something else.
Yes.
I'm going to reorient our camera so that we,
Okay.
is that good?
That's fine.
All right, so we have a reorientation of the camera, which means you will probably see the view
Hold on to your chairs.
M42.
twist sideways or spin in place. There it goes. Well, if you want to have a look at what Tom is doing, let's get to our dome view. This is me over here on the right-hand side, but we have Tom up there on the ladder. And this is a view inside the 60-inch dome. What I can't show you because my arm is not long enough is there is, just where the telescope is pointed, there is a dark strip of sky. That is where the dome is actually, the shutter is actually open, and the telescope is looking through the roof at the actual sky. And there is the moon, which is getting higher and higher up in the sky and further over to the west, because the Earth is rotating. The Earth rotates from our perspective eastward, and everything seems to move westward as we look at it in the sky. So this is where we get to see the telescope actually changing position. The telescope itself is quite quiet when it moves. The dome is a little squeaky. I'm not even going to try and talk. Just get squeaks.
it better be pointed north.
Right.
Like you said, the mount cost enough that it should.
Right. So what is that mount made of? Concrete or is it steel?
That's a steel tube,
Okay.
and then it's got a Paramount MX on it,
Okay.
software disk. So,
Bolted onto the foundation or dug
Yeah,
through the
it's-
foundation?
it's bolted into a base isolator.
Okay.
Not that it matters because there's nobody in there.
Well, yeah. The vibrations are great.
It's a granite mountain.
Yeah, it. Yeah, but we have earthquakes every so often.
Well, the earthquake, we've had one earthquake when we were running
Oh.
and scared the heck out of everybody, and they shut up everything and operations are done.
Oh wow.
Because we can't have anything accidentally fall from somewhere.
Yes, very true.
land
Wow,
on the
when
mirror.
was that? That must have been a while
It was
ago.
Michael Rudy had it happen to him. It was over
Oh.
a year, 2 years ago.
2 years ago, an earthquake up here on Mount Wilson. That'd be a little nerve-wracking.
It was a little nerve-wracking.
Earthquakes are always nerve-wracking. My cats really, really don't like them.
No.
My chickens could not care less. The cats,
Chicken goes, I can fly. Not far, but I can fly.
not my chickens. They're a little on the heavy side.
Go on the heavy side.
They're well-fed chickens. All right.
So we're gonna kill the lights.
Telescope still moving.
Yeah, you can put it on you if you want. Maybe I'll tell you when we're close.
Am I?
Oh, you can put it on
Am I
me.
off?
How exciting. People can see me again. Yay! Welcome back to a view of me in my hat and my warm scarf because it's quite cool up here. They've just turned all the lights off, so I can't even see where my that's okay. I got a flashlight. The thermometer. And the thermometer is reading 38 degrees, which is around 4 degrees centigrade. So it's a little chilly up here. So these masks are actually for warmth, which is quite nice. I'll put my hands in my pockets. But we are getting ready to look at, what are we looking at, gentlemen? What's our target right now?
M42 in Orion.
M42
Getting a
in
little bloated.
Orion. So we can ask our audience if you guys know what M42 is. Okay, so Sebastian Michaelis? Michaelis says, hi, Tom.
Who is it?
Sebastian?
Sebastian?
Yes. And then Mike Rudy said the 100-inch dome made one heck of a racket in the earthquake. Oh, that would. As you can tell, the domes are a little rattly. How big is the CCD behind the scope? Is the next question coming in from YouTube.
How
How
big is
big?
the CCD? Oh, goodness.
4/3 chip, whatever that's a size.
The attic, too?
The attic is 4/3. The refractor is APCS, and the next step up is full frame, 35 millimeter. And they kind of go 1,000, 2,000, 4,000.
Yeah, so
Okay.
This thing, physical, I can look up the actual physical units of it, but we'll, after we do the image of the object.
Okay.
Okay, so do you feel that we're in focus, or should we?
That's a trapezium, let me just.
It's actually, it was much worse than this one time, I remember.
So we're looking at now
At least they're 4 stars.
M42,
This
which
2
is
minute exposures.
Okay, 2 minutes.
the designation given
That's why the stars are getting.
by Charles Messier, or I'm
Oh,
not
this
sure if
one's
Messier made the catalog and then named it his numbers,
I dropped it down.
but M42
Is that?
is the famous Great Orion Nebula, also known
I
as
might be out of-
NGC
No, I don't know.
1976. So this is a star formation nebula within the boundaries of the constellation of Orion. And I know a lot of people kind of envision patterns that bright stars make in the sky as the definition for a constellation. But modern astronomers have a slightly different take on the word constellation. I'm just going to pull this down so you can see my face. A constellation to modern astronomers is not just the bright stars that make a pattern, but it's an actual patch of the sky. Just like the United States is divided arbitrarily or politically into different individual states, and there are boundary lines between states. And for the most part, those boundary lines are imaginary. Sometimes there's a river, maybe there's a signpost or a fence, but for the most part, it's kind of an imaginary but political designation. So constellations in the sky, there are 88 of them, and the boundaries are invisible. There's no real line out there, but astronomers know kind of where the boundaries are in their maps, and then they can say this area is going to be known as Orion, this area is known as Hercules or Perseus or Andromeda or Cetus or Draco. Right now we are looking with the telescope at the Great Orion Nebula. Now, before we go and have a view through the dome, I'm going to show you the pattern of stars that makes the constellation of Orion. And it's up in the sky in Southern California right now. So if you want to head outside and go and have a look, I will show you what it looks like. So let me just, okay, hang on. That works. Now I can't see anything. Woo. Okay, I'm going to go over to a software program called Stellarium, which is kind of like a planetarium you can get for your computer, your desktop. They do have a web version, but the version you can actually download for free from stellarium.org is much more robust and has a lot more information.
Okay.
The mobile app for Stellarium is not free. I believe it's around $10, and I don't have it, so I can't give you a review on that. But what I want to do now is kind of go over, right now we're looking at the sky, and then down here is the ground, and right now we're facing south, or rather the computer program has us facing south. But the neat thing about Stellarium is you just click and drag, and then if you're facing southwest, almost straight up are the really 7 bright stars that make the familiar pattern of Orion. So I'm just going to zoom in a little bit, and you can see there's Beetlejuice and Bellatrix, Rigel, this one over here is Scythe, we have Alnitak, Alnilam, Mintaka, Alnilam's the middle one, but below these 3 here are Orion's belt. And to give you an idea kind of the stars that are connected with each constellation, and also the constellation names themselves, I can add these on, but Orion is known as a mighty hunter, and he has a belt. These 3 bright stars in a row make Orion's belt, and these 3 beneath the belt signify his sword, or his scabbard, where he stores his sword. And so this is what we're going to look at. You'll notice that that center one, what looks like 3 stars in a row, that center one is very, very fuzzy, rather indistinct. And that's because it's not actually a star at all. It is a nebula. And a nebula is the astronomer's word for giant cloud of gas and dust in outer space. So we are going to head over to the attic view.
Go ahead.
And we have
Trapezium.
the trapezium. Dun, dun, dun. And you're like, wow, that was unimpressive. The trapezium, it'll get better, don't worry. The trapezium is the name given to the 4 very bright, newly formed stars that are kind of embedded within that nebula, within that huge cloud of gas and dust. So here we have the 4 of them. They are surrounded by gas and dust, which is why they perhaps don't appear as bright as they might otherwise would be if they didn't have all this dust kind of obscuring some of their light. They are also 1,500 light years away, so they are really, really far away, as is the whole nebula. But are you going to zoom out or zoom in, Chris?
I'm going to increase the exposure time.
Ooh, increase the exposure time. Super exciting. So by increasing the exposure time, we begin to see more of the nebula itself. And you can see Chris is puttering around changing the parameters of what he's actually looking at here. The light from those stars is now getting completely blown out, but the stars are much, much brighter than the glowing gases that surround them. So the light from these stars will actually energize the atoms of the atoms of the gases surrounding them. And we have a color balance issue again. Yeah, it usually corrects itself after a minute or two. It's not actually green out there. But this is, you can see now the nebula surrounding these 4 bright stars. And there are patches of the nebula that are a little more dense. There are some areas that are a little more wispy. It's a cloud, just like clouds here above our heads during the day and night. Sometimes the clouds seem very thick and heavy, and sometimes they seem very wispy. These clouds in outer space are the same, but you can see the nebula here, and if you imagine what color you're seeing, I think for the most part you'll agree once you have a good look, it's kind of a rosy, sort of warmish red. And that red color is ubiquitous.
I'm stacking.
Whoops.
Reset.
He was stacking images, so you take a picture, take another picture, take another picture, stack them all on top. But someone went up there and moved the camera.
No, there's not enough stars to stack,
Oh.
so the program gets lost.
Ah.
It can do it sometimes, but it seems
Technical difficulties with the stacking program. But the wispy redness, indicative of hydrogen gas or hydrogen atoms. So these atoms in the gas cloud are energized by the light they receive from these 4 bright stars, and they will absorb some of that light and then re-emit it. They re-emit the light at wavelengths that are characteristic of that type of atom. Different types of atoms will emit different colors of light, different wavelengths of light. 90% by number of atoms of the known, observable universe is hydrogen, so we expect to see a lot of red when we're looking at things out there in space. And we do. This gas cloud has a lot of hydrogen in it. If you see any kind of peachy, yellowy color, that's indicative of helium. And the green is going to be doubly ionized oxygen. So it's kind of neat. Astronomers can look at the colors surrounding bright stars and say, oh yeah, there's hydrogen, there's some helium, there's some oxygen out there. They get really good at this. For more, I would say, exotic elements like silicone and neon and iron and sulfur and things like that, that we know exist in space and in these clouds, there's not as much of, wow,
it's confused.
this poor computer program.
All right,
There's not as much of that stuff, so you have to really have your exposure time very long to collect that light, or light indicative of rare atoms. But all of this stuff has been determined to exist in nebulae out there in space. So it's very, very careful, very tedious observations. But if you have someone with enough patience and enough skill, you can certainly do it.
Just trying that. So for some reason, oh no, didn't like that. Reset.
Reset.
It's going above 5 seconds. Just doesn't.
Oh, it
it's
doesn't like.
rotating. Why is it rotating? That's odd.
We could live stack on this one. I haven't done it.
Are we zoomed out as much as we can be on the attic, Chris?
Yeah, this is the full.
Yeah.
Full frame.
Full frame.
Okay, let me try stacking again. Try this. See what that is. Yeah, it is. It's. That's weird.
just not behaving so well?
So those aren't really good centroids. I mean, they're big centroids.
So how would you classify the seeing tonight, gentlemen? Poor, fair,
It's
or
not the worst I've ever
good?
seen.
It's poor, it's not abysmal.
Yeah.
It's poor, it's not abysmal.
All right. We're gonna. You want me to?
Do you want to
Killed
try
with
light
faint
stack?
praise, yeah.
Oh,
I've
there's
never,
a,
I've
okay.
never tried light
All right, we're gonna
stack.
bring Richard's.
Okay, this is a wider field view. This is with the 5-inch refractor. And I believe we're gonna try stacking
Let's try light
with
stacking this.
this
Here we go. Let's see what
camera.
happens. So what's the current exposure time?
20 seconds.
20 seconds. All right.
20
So that's
seconds.
something else to point out is that. Oh, that was good. That worked. So it's got more stars to deal with, so it can actually.
Yeah,
figure out.
it can, the more stars it has, the more points it can use to overlap the images. So when you stack them, they're stacked neatly on top of each other instead of kind of sort of beside each other and not really on top of each other, and then it's like triple vision or something. But here's when you can really see some of the other colors come out. So hopefully that you can see this down the pipeline in YouTube land, but there's definitely red. I see a lovely red ridge on the up, you know, on the left-hand side
Yeah.
by the 3 bright stars, not the trapezium, but the 3 brighter stars kind of down the center of the image there. And then we also have a little bit of creamy in there that would be the helium. And if you can cross your eyes sideways, maybe you can see, or pretend you think you see a little bit of green in there for the oxygen. It has been said that the trapezium stars are quite young. Can you talk about the technique that tells us the age? Gentlemen, any one of you want to get a handle on that? The technique to tell the age of the stars of the trapezium.
Oh.
Metallicity we have.
It would have to be so. I'm not
And
an
if
expert
they're-
in this either, but
Chris usually does supernovae
yeah, I'm at the other end when they blow up.
when they die, and I did meteorite studies. So this is neither of our areas of expertise.
Yeah, I don't think you can tell precisely what the age of these stars is, and that's usually a very hard thing to do. You can talk about the population of stars. If you have a cluster of stars, it's easier to figure out their age. But I'm guessing they just, because of the spectral type, what kind of the type of stars that these are, they can only be a certain age. Otherwise, they would
This is
have
true. Yeah, if
evolved
they're
up from
very
this-
massive stars, they can only live to a certain age before they go supernova. I'm not sure of the mass of these stars, but another indication of age is the metallicity, which here would be the same presumably as the rest of the Orion Nebula because they formed from the Orion Nebula. The metallicity content of a star is that percentage of the composition of the star that is neither hydrogen nor helium. So back in the Big Bang, way back in the day, hydrogen and helium formed as a result of the Big Bang, and a little smidge of lithium. All of the other elements that exist in the universe formed as a result of thermonuclear fusion in the core of stars. The carbon that you are made from, the iron in your blood, the oxygen you breathe, all of those formed within the cores of stars that have exhausted their nuclear supply, nuclear fuel supply, and have gone supernova or planetary nebula and spewed this material through space. And this material that kind of got spewed through space then gets reincorporated into nebulae. It's kind of like cosmic recycling, and seeds those nebulae with the heavier elements that formed in more massive previous generations of stars. So this is how we get things like iron and sulfur and neon, which did not form in the Big Bang. The only mechanism to form these atoms is as a result of, I guess, stellar evolution and stellar death, if you would. So looking at the content and how much of the composition of these stars is what is heavier than hydrogen and helium can give you a rough indication of age. But again, that's not my area of expertise. I did isotope studies and meteorites and other samples, and Chris is an expert on type 1A supernovae. So we have some more questions coming in. Oh my gosh, look at all these questions. This is great. Would you be able to repeat what exactly it is that we are looking at? Absolutely, I can do that. The element production during a neutron star merger. Yes, there's always neutron star mergers will end up as a cataclysmic event, a hypernova, and that is a very energetic event that can produce a lot of fast neutron capture, fast rapid proton capture, and produce a whole bunch of new elements. But as for what we are looking at, this is the Great Orion Nebula, known as M42, the 42nd object classified by the Messier, or cataloged in the Messier catalog. And to give you an idea of where it is that we were looking, Kiana, hang on. Gotta switch over. Okay, so we are gonna go to Stellarium, which is a piece of software that I downloaded onto my computer, and this is planetarium software, if you would. Here we are, that rattling you hear, by the way, is the dome in the wind. But here we are facing south at Mount Wilson Telescope here, and up and to the west, we have the brightest star visible in the night sky, and that is a star called Sirius, after whom Sirius Black in the Harry Potter movies and books was named, I will have you know. And over a little to the west, we have the constellation of Orion right here. So I can bring on kind of connect the dot lines of the historical constellations and bring up their names. And I don't think I have a way to bring up the boundary lines for the IAU astronomical boundaries, but I can bring the some of the images or the artwork that's often associated. I always like the fact that there's a unicorn right behind Orion, ready to poke him in the shoulder. But, you know, Monoceros or Monoceros. I don't speak Latin, I'm not sure how to pronounce that, but these 7 stars are super famous. If we zoom into those, we have Beetlejuice, which was in the news last year because Beetlejuice was getting quite dim. Beetlejuice is a variable star. It gets brighter and dimmer and brighter again, and it was getting dimmer and dimmer and dimmer and dimmer, and all of the astronomers, or many of the astronomers watching it, were like, oh my gosh, is it gonna go supernova? Because it is massive enough that it could. And then it started getting bright again. But here we have Beetlejuice, here we have Bellatrix, after whom Bellatrix Lestrange is named. Rigel, Scythe is down here, Alnitak, Alnilam, Mintaka, and the Orion Nebula is this middle star-like object, but you can kind of see it's not a star because there's fuzziness around it. So if we zoom in a little closer, you can see the nebulosity around this whole area, to be honest. But the trapezium are right in here. That is what we're looking at, that region of the sky. So if you go out and look up from a truly dark sky, somewhere far from LA, the city lights of LA, you can actually see this fuzziness for yourself. It's quite wonderful to see if you're ever in a position to go for a weekend. If you're in Southern California, Joshua Tree National Park is a great place to go. Death Valley National Park, also an amazing place to go. Both places you can camp, which you can socially distance when you're camping. Both places are far from city lights. And they're just amazing places to go and visit during the day, as well as the night skies are really dark. Don't plan your camping weekend during a full moon, because that full moon will wash out all of these fainter objects. You want to see if you can get either a third quarter moon or a new moon. And then you get to see views something like this.
So that is now stacking, and we are up to 36 seconds total.
36 seconds total. So this is where you're going to be able to start seeing the color of the nebula itself as more images are kind of stacked on top, and visually the kind of complexity of the structure of the nebula and the colors start coming out a little better.
So I'm going to try putting the exposure time up a little bit, because I figured out what was wrong.
So here's a couple questions. Is the new Godzilla constellation from the news a real thing?
What?
I have not heard about that.
Heard of this?
A new
Tell
Godzilla
me more.
constellation. Tom, Richard, has that come across your feed?
I have not. Maybe King Kong killed it.
Yeah, King Kong got it. I cannot answer. I am sorry. I do know that the IAU recognize and have recognized 88 constellations since the 1920s, I believe. They were kind of written in scientific academic papers. Although the IAU, and I don't know if this is what you're referring to, the IAU is now recognizing the constellations and the lore associated with the stars and objects in the sky from other cultures. So the IAU, the traditional 88 constellations are primarily Greek, Greco-Roman constellations, Hercules, Andromeda, Perseus has the head of Medusa. They're very European, Greek and Roman. But it is not the only place where constellations.
So we're going to go on, I think, to another object now.
Okay.
Clownface Nebula.
Ooh, we're going to go to the Clownface Nebula.
So you can keep on.
I'll keep talking about
this if you want.
constellations.
Sure.
Yeah. Barbara just answered. It was something about a constellation based in the X-ray.
Using the orbiting Fermi Gamma Ray Space Telescope, an international research group that includes NASA researchers has named a constellation of gamma ray emitting stars Godzilla.
Okay. Yeah.
According
Great.
to the movie. Okay.
Gamma ray
So that's
emitting
probably,
stars.
so that's not going to be a big constellation on the sky. It's going to be a collection of stars, probably in a small part of the sky, that are emitting gamma rays for whatever
Is that
reason.
gamma or gamma rays?
Gamma
Gamma
rays. Gamma.
Gamma is a turtle.
Nerd.
Flying turtle.
Okay. You know what? I'm going to put.
If we have X-ray
let's go back.
constellations or gamma ray constellations, I
can
suppose we
now
could have different ones.
go on
But as
to
I was
the-
saying, the IAU is finally recognizing the fact, a long time coming, too late, or too long actually, that other cultures have a really, really rich history of stories that they told about patterns that they saw in the sky. So the native people of North America and Central America and South America, Australian Aborigines, we have Filipino stories, Korean, Chinese, Mongolian, Chinese certainly, I mean Indian, you name it. Everyone looked up at the sky and everyone told stories about what they saw. So, yeah.
I'm going to put the lights up if you want to show the
Sure.
view of.
Of the dome? Let's go to the dome view. Oh, bright lights. There we go. Woo. Night vision. So Orion is just one of the 88 constellations, and that is from the Greco-Roman tradition. For the most part,
Let's see if it's there.
Orion, or those stars seen as a warrior or hunter, is consistent with many, many sky cultures. Certainly the Armenians saw the stars of Orion as Haik, the founder of Armenia, who was a warrior. and a leader. So there is some groupings of stars that are consistently thought of as the same thing. One of them is the Seven Sisters, also known as the Pleiades or the Pleiades to the Greeks. But as far away as Australia, those groups of stars are still called the Seven Sisters. And my understanding is that the Australian Aborigines were mostly isolated for at least 15,000 years prior to the colonization by Europeans. For sure, they would be visited by those in kind of Southeast Asia, but the culture has the Australian Aborigines have a really, really rich and complex sky culture, talking about all the stars and the constellations and explanations for what they see and explanations for or matching up with what they see in the heavens with what happens with flooding and with crop planting, things like that. It's really quite amazing. So we're here in the dome. It is still cold. It is still hovering in the high 30s, just above 0 Celsius. Whew. And we are looking for the Clownface Nebula, which is a planetary nebula. And I want to say Draco? Not Draco. What constellation is the Clownface Nebula in? I knew this. I was reading about this the other day. Observe. Nope. Ugh.
Gemini, I think.
Gemini. No.
Okay, I'm gonna bring the lights down.
Lights going down. One.
All right. Well, there it is.
It's tiny. I said it's tiny.
I don't know where all the cheat sheet went, Chris. Not the cheat sheet, the list. Is it in sessions?
No, it's under observing lists.
Oh, how do I
Observing
clear it?
lists. Lists. Aha. And then we have the Clownface Nebula. All right. So the Clownface Nebula, also known as NGC 2392, is a planetary nebula in the constellation of Gemini. And there's Richard standing up. Do we have anything yet?
We're just gonna center and focus and do things like that. So
There we go. They are centering and focusing. And I will tell you more information about this. This is a different type of nebula than the Orion Nebula that we were just looking at. The Clownface Nebula is a planetary nebula. It is a cloud of gas and dust. It is much, much smaller than the Orion Nebula because this isn't many hundreds and thousands of times larger than the solar system from which stars form. This nebula was produced when a star, a middle mass star, medium mass star, much like our sun, finished burning or fusing its nuclear fuel and then went out. So this is kind of like the last puff off of outer atmospheres that a medium mass star will shed into space, and it's kind of like an expanding bubble that will eventually dissipate into space. But this is a misnamed phenomenon. William Herschel first observed this nebula in the late 1700s, 1787, and he had seen things like this for a few decades, and he thought that it might have been another planet. So in 1781, I think, Uranus had been discovered. First planet to be discovered. All the other planets have been known since antiquity, right? Since prehistory. Mercury, Venus, Mars, Jupiter, and Saturn, you can actually see them in the sky. They look like stars. They don't move in the same manner that stars do. But Uranus you can't see without the help of a telescope. Neptune also. So Uranus was not discovered until 1781. Might have been 1783, but I think it was 1781. And when Herschel was looking at his objects, he noticed this was kind of round, kind of bluish green, the same color that Uranus was. And he thought, oh, well, maybe these objects are planets. So he did some more research, realized they weren't planets, they were nebula, but dubbed them small spherical planetary nebula, because he thought there may be a planet inside, or they had the look of a planet. So it's a really poor name, poor choice of name, but we're stuck with it. Why it's never been changed, I don't know. This is a planetary nebula, has nothing to do with planets. It is the puffed off outer layers of a dying medium mass star.
All right, I'm just bringing the exposure up. And we'll be ready.
And Chris is bringing the exposure up. This is super exciting. I know you're just all out there sitting with bated breath.
Well, I'm taking the enthusiasm a bit.
I'll start stacking it. It should come out.
Keep in mind that the atmospheric seeing is not ideal tonight, so
Also
the
got a
view that we are getting is
Yeah.
not what it could be, and certainly not what you're likely to see when you Google, you know, the Clownface Nebula, which you can do right now if you want. I'd recommend looking at our version first.
Okay.
When you're looking at images online, a lot of them were taken with the Hubble Space Telescope, which is orbiting the Earth above the atmosphere, so it does not have the blurring effects of the atmosphere to deal with. Also, the images that are professionally produced have their colors enhanced. So we know exactly what color and what wavelength the light is. And astronomers that are publishing these, or sites that are publishing these images, bump up the colors. It's
We're rejecting all of them.
the colors are there, they're just not as brilliant before basically being photoshopped. But I mean, if you look at glossy magazines, all of the models, or many of the models, will have had, you know, a little bit of airbrushing, a little bit of coloration. They look like they're glowing a little bit. Well, the same is done for many of the astro images that you see in these glossy magazines. We have not done that. So you get to see exactly what they would look like through our big telescope.
You can do it anytime.
Anytime. All right, let's go to the attic view. That is not the attic view. There, that's the attic view. So here is our Clownface Nebula. Does not look anything like a clown to me.
Doesn't look happy.
Doesn't look happy, like a big cyclops. The thing at the center is the white dwarf. So the white dwarf is what is left over of the core of that medium mass star where the thermonuclear fusion had been taking place. A lot of the material kind of collapses down onto that core, and that core is super, super, super hot. It's tens of thousands of degrees Kelvin, and it is emitting a lot of ultraviolet light. And that ultraviolet light is what energizes the gases that have been expelled from around it, and it causes those gases to glow. So you're not seeing a really good version here. Are we stacking this at all?
We tried.
We're trying. We're trying to stack.
It doesn't have very many stars to work with, so I'm just trying to see if I can reduce the amount of light.
You got the moon up there.
Yeah, the moon, when you're looking at things that are really quite faint, if the moon is gibbous or full, it's a real pain. It's just washing out all of the fainter images. Now, this particular nebula has a visual magnitude, or an apparent magnitude, of +9. With your own eyes, you can see down to a visual magnitude of +6. And that doesn't make much sense. If you've never encountered the apparent magnitude or the visual magnitude scale, it starts off with Hipparchus, way back about 150 BCE, and he came up with the idea of classifying stars based on their brightness. And the brightest stars, like Sirius, were given the first classification. They came in first place. They were the brightest. And not so bright, but still pretty bright, were the second class stars. They came in second. And third class stars were more faint, fourth class, fifth class, and then sixth class or sixth magnitude stars were the very faintest stars that you could see. And these are stars that you can only see from a truly dark location like Joshua Tree or Death Valley on a moonless night. And these are stars that you also have to allow your eyes to dark adapt in order to be able to see. These are really not easy to see, and that's sixth magnitude star. This nebula is a 9th magnitude star, so it was never viewed by our ancestors that lived thousands of years ago. I mean, the planets, many of the stars were viewed by our ancestors. Not this puppy. At 9th magnitude, the only way you can collect enough of its faint light to form an image to see is with the help of a telescope. And I know a lot of astronomers view telescopes as light buckets. I kind of use them as light, I like to describe them as light funnels. So if you want to take a whole bunch of water and put it into a little tiny glass, like a bucket into something the size of, say, a spice jar, a funnel is a super helpful piece of equipment. Get all of that water down into, presumably it's a very, very tall spice jar that can hold all the water, but it kind of funnels all of that water down to a point. Now your eye is a very small point and will only let in a little bit of light, but if you have some sort of collection device that could then funnel all of the light that is collected down into your eyeball, that would be pretty cool. Then you could collect more light and focus it down, and then you could see fainter objects. And that is exactly what a telescope does. It collects the light, focuses it to a point, and then you look at that point with the little eyepiece of the telescope, which is like a little baby magnifying glass. And there's some interesting things happening over beside me. They are putting a plastic sheet over the monitors for reasons I do not understand.
We're looking for something a little bit more opaque.
Yeah.
Oh, you're trying to dim down the monitors.
Yeah.
Oh,
Helped.
Nope.
Nope. Okay.
nope, I don't think it helps so much. But I am beginning, so you've been stacking for a while, yeah?
You're not stacking.
They're not stacking, because I'm pretending that I can see some green here, but I don't think I'm seeing any green.
Right.
I think it's just white. My eyes are playing tricks on me.
Just as a Hail Mary.
Let's try binning. All right, all the way up to 8. Let's see if it works. Let's see if it does any different.
Fantastic. Okay, we have a comment on YouTube. Kiana says that they have an assignment to do based on this live stream. Could you please explain what you mean by stacking?
Ah.
Absolutely.
Okay.
You want to take that over, Chris?
I'll take that over.
Awesome.
All right. So, hopefully you've noticed when we increase the exposure time, you can see more details coming up from the image. Hello. The problem is if we try to keep putting the exposure time up and up and up and up, a few things happen. One is the background also goes up, and this telescope is particularly sensitive to the background light, which is the moon. Yeah, we've got a bright moon very close. So if we just keep on increasing the exposure, you're going to get washed out by the background. Then the other problem is the telescope doesn't track perfectly well. So even though it's pretty good and things don't seem to move very much, if we let this thing go for about 30 seconds, the stars would start to look more like little comets. They would have little streaks.
Yeah.
So what you do is you take a short exposure, save that image, take another shorter exposure, put that on top, and take another one, put it on top, take another one. And what I mean by put on top is because these images are just a bunch of numbers, really, they're just bits and bytes on an array, you can take an average. You can say, okay, I'm going to take this image, I'm going to take the average with this image, I'm going to take another average with 3 images, I'll take an average with 10 images. And what that does is anything that's real, like a star, the nebula, and all that sort of stuff, that tends to grow in significance, and the background noise, which is random, gets averaged away, and so you end up with something that looks a lot better. But the software needs to have enough stars in the field of view to be able to say, because it has to not only take the image as take the image, and then it has to rotate it maybe a bit and then move it this way so that the next one you get is, am I doing this right? Lined up. This is hard to do on a camera. So they're lined up, and so when you take the average, you're actually getting everything lined up in the proper place.
And
So-
he's talking about the shifting and whatnot, and that is due to the atmospheric seeing, which is the blurring and the shifting around caused by the atmosphere.
And also bad tracking by the telescope. That'll do it too.
Yeah.
All right, let's show you guys what stacking does. So I'm going to bring Richard's telescope over because since he has a wider field of view.
Well, I can't see it. Hang on, let me
Yeah,
go back.
sure.
This is the cool part.
So how well can you see that? I think you can sort of see it.
Can you zoom in?
I'll zoom in a bit more.
So this is zooming in with a 5-inch refractor. And we've got
Better?
the nebula pretty much centered. There's a fairly bright star just to the right. But the nebula here is kind of a greenish blue. And that is the Clownface Nebula, which doesn't look anything like a clown.
Well, whatever. But the point here is it's been stacking, that's 40 individual frames, each one being 20 seconds. So we've taken 40 20-second
exposures.
20 exposures, and
And
we've
then
combine them all together. Now you may notice that even with the stacking, that big bright star in the upper right, this one here is looking a little not quite round. So some of those stacks may have been, the shift may have been incorrect. And so when you added them together and took the average, you get a little bit of a blurring effect. But certainly the nebula itself sort of pops out a lot more, and the background noise has been decreased. Did that answer the question?
I hope so.
I hope so. If not, just keep asking, because
It's like if you had, it's like if you had a stack of papers, right? If you tapped them against the table and had them all lined up perfectly, it would be great. But if you just throw things together in a stack and like the corners are all kind of not aligned properly and it's just like this stack of paper you're carrying over, then, if you had writing on the paper and you couldn't, they wouldn't line up. Wouldn't be as good.
so that's 5 seconds. Let's see what happens if we go all the way up to like, I'm going to put the gain down and put the exposure up. So hopefully that will make the background not quite so bad. So another thing
we'll see.
another thing we can do is not only change the exposure time, in other words, how much time we allow the camera to pick up the light.
You're welcome.
We can change what's called the gain, and for anyone who does photography, this is like changing the kind of film you would have had to a different ISO.
Speaking of that, we have another individual, Jinji Pinji,
Better.
Jingping. Does the visible scope work like a camera lens? Shrink the aperture for a deeper field, a deeper depth of field for images. I was about to say, we don't have depth of field. Everything's basically at infinity here. Even the moon, the closest thing we have was the moon, and that's 380,000 kilometers away. So you're not going to be able to have one versus the other.
I think this question might have more to do with photography, and the answer is we can't really change the aperture easily. You could, so this thing is a big mirror, it's 60 inches across, and you could get a cover for that and, like a big circular cap and put a hole in it And they did do that if they were looking at a really, really bright source and it was too bright for the telescope. You could do what's called stopping it down and decrease the area of the telescope to give you a better view. Okay, so changing the gain, I think, has helped a lot because now we can see a little bit more structure inside.
Yeah, kind of the second ring around it. Yeah.
And this is why it's called the clown face, because there's your smiley face right down here.
Really?
So it's a smile. It's the Cyclops.
The smiley Cyclops
so you got
clown?
a Cyclops with maybe a beard, a goatee, maybe.
I don't.
know.
Seriously?
I
That's
don't-
what they came up with?
Well, it used to be called the Eskimo Nebula, but we don't call it that anymore.
We call it Inuit Nebula, and they
Called
do have the
Inuit.
beautiful, stunning fur. What do they call the fur around their hood?
All right.
It's the sunshine ruff. That's it, the sunshine ruff that the
I'm
Inuit build.
Putting this up to 15 seconds now, and we'll see how well the telescope can do and how the background behaves. So, we have to wait 15 seconds between each frame.
It's an exercise in patience. Whoa, that was a bright background.
Well, it's also because you're exposing for longer, so you're getting more of that background light. This might not be
Ideal choice.
the right thing.
See more color,
The cold is beginning to seep in.
grainy, but
Make it brighter, and it shows it better on that.
So this way.
Yeah, it shows it better on hers.
How's that look? Yeah, that looks a bit better.
Yeah.
At that, but now you can see there's other sources of moonlight, I think, coming in here. You'll notice the
Yeah.
background gets brighter as you move from one part of the image to the other, and I suspect that's because that's the way the moon.
The moon, that's the direction the moon would be in real life.
Yeah.
The
Let's just for fun, let's try stacking again, just to see what happens. Come on, you can do it.
It'll say no.
Denied. Let's try. Come on. One more.
like 4 stars there.
And
I understand it's got to make triangles.
it does that.
That's how it does knows
Yeah.
the rotation as well.
All right, it's not.
And
gonna
there's
do
not
it.
enough stars to make the.
Not
triangles.
happy. Should we find a different target?
We could find a different target.
I know there was one that you were
certainly.
thinking about earlier.
M82.
We could try M82. I think that would look decent.
All right, M82 being the galaxy.
Yes.
All right.
The star-forming galaxy.
The star-forming galaxy. A galaxy that is famous for being where many stars. Oh, the alarm's going. M82 is not on my list. So let me give it a good search. Boop. Oh, we can go back to the dome view and you can see the telescope moving around again while I look up M82. Which is Bode's Nebula? Oh, it was on our list. It's not a nebulae. Oh, well, it was when Bode thought it was. It's actually a peculiar galaxy. Also known as the Cigar Galaxy for obvious reasons, has been spectacularly disturbed by a relatively recent encounter with another galaxy nearby called M81. And by disturbed, they would mean gravitationally disturbed, or gravitationally interacting with, and displays conspicuous dust lanes and heavy star formation. It's the prototype irregular starburst disk galaxy. Discovered in 1774 by Johann Elert Bode. Once again, we have the dulcet tones of a rotating dome.
She's old and cranky.
No, she's old. At 120 years now?
1908. So 113.
Well,
Almost.
Yeah. I was about to say she probably came online a little bit before the telescope did.
Oh, the dome. Yeah, they took them 3 years to build this.
3 years. You know what? I think it would take 20 these days.
And most of this all came up on Mule.
Yes. The fact that most of the pieces of the dome and the telescope and the mirror itself were hauled up the mountain in the early 1900s via mule train, donkeys. That's pretty amazing. So there's a question, Chris, about stacking visible images with radio or IR observations. I know that they do this. A lot of the images coming out of the Hubble Space Telescope or the Space Telescope Institute will have visual images and then ultraviolet and sometimes X-ray, and they do overlap them and color code them for different wavelength ranges. I don't know if we could do that here. Certainly this telescope cannot measure really IR or radio.
Yeah, it's so another.
Here, I'll let you sit down. I'm just gonna get downstairs.
So one of the other advantages of this camera that we're using, this CMOS camera, is each pixel on the camera array has its own filter. And this is called a Bayer filter. And if you looked really, really, really closely at it, you would see a red pixel, a green pixel, and a blue pixel. This sort of red, green, green, blue. And that's repeated over the entire chip. And so the software, when it takes that image, it can combine the red pixels, or I should say the pixels with the red filters, the pixels with the green filters, and the pixels with the blue filters, and make a composite color image right away. With CCD cameras, normally what you do is you would take a picture of the entire frame through one red filter. You would then change the filter to a green filter, take another picture, change it to a blue filter, take another picture, and then after the fact in Photoshop, you could combine those together to make a nice composite color image. And certainly the big telescopes like the Hubble Space Telescope and other ones like that, they will often do tricks like that, but not necessarily with red, green, and blue. They might do it with some ultraviolet light, maybe some hydrogen, the special filter that sees hydrogen, and that sort of thing. And so you can get what they call false color images, where they kind of assign one color to a different kind of wavelength in the image. And so it's not what your eyes would see, but it does give you some nice images that give you some information. You can see where the really, really hot, energetic stuff that's making ultraviolet is versus, you know, the sort of cool gas where you find infrared. So you can combine all those together. And with radio, it's sort of the same sort of thing. You're looking at a different part of the electromagnetic spectrum at the very long wavelength end. And you can do the same sort of thing. You can assign a color to one channel. In this case, they usually refer to bands, just like you would when you use your radio. You go to a specific channel, which is a wave band. They have different bands with the telescopes, and they can combine those bands using different colors. So they can show you a color image that your eye would never be able to see because we don't see in the radio part of the spectrum. So I hope that answers your question. And we are, I think, pointed at the right place. So we are going to turn the lights out and see what we can see. All right. Yeah.
That's what we see when there's lights on.
That's what you see with the 15-second exposure and the lights are on. So it's bring this down to something like 4 seconds. Hi, game.
Yeah,
It's cold.
it gets a little cool when
A little cool when you're just sitting here doing nothing.
Yeah, the wind's coming through that.
Oh yeah.
there we are.
Oops. Okay, just changed the thing on me.
And we have enough stars we can start stacking. So
I remember as an undergrad doing jumping jacks in a dome in Canada in January.
We
When
were-
the snow was swirling through, and
we were
was
running
so
the
cold.
16-inch
I
telescope. It was
guess
23
that's-
degrees. And we
that-
didn't realize that moisture had settled between the keys. And when we were pushing down one key, we were actually pushing down 5 keys. We're going like, why are we getting errors? Knocking ice out of the thing.
Out of the keyboard? Oh, well, we weren't using any computers. We had put a photographic plate, a glass plate, onto a spectrograph. We were slewing back and forth to get a spectrum. It was back in the old days when dinosaurs ruled the world.
When they ruled the world, yes.
Yep. Yeah.
I'm
There are
gonna
many scopes
try-
that use photographic plates
Yeah,
anymore.
there we go.
We're talking about putting a spectrograph on this one.
Okay, so I'm gonna do the same trick I did last time and reduce the gain.
That moon is really bright.
Put out the
It's
like-
actually pretty dark out here.
It is pretty dark, but the moon, I can see it just lighting up the edge of the dome.
Yeah.
Oh man, I can feel that wind coming down in here.
See, and that's one of the differences in the telescopes. The light is actually probably reflecting a little bit, even though it's shrouded. The secondary, the refractor is completely sealed, and it's pointing
Yeah.
a different way. It doesn't get in there.
Okay, well,
Might be time for another hot chocolate.
what's that?
So I can't tell what we.
Oh, it's
That's what I'm talking
my
about.
showing slightly different.
Yeah, it's right here.
They're just listening. This microphone picks everything up, so our audience is listening. Oh, I'm glad that made sense. Jinji Pinji, or Jingping. I am not sure of the pronunciation.
Oh,
The opposite of that one, yes.
So we turned the dome, and all of a sudden, it's freezing in here. Just
it's clearly coming from the north.
Pointing
Wow.
to the north.
All right, that's good. A little bit further. A little more, I think.
I can't see what the temperature is. I don't think the temperature has actually changed much.
No.
Exactly.
But it seems that much cooler. We're all getting our hats on and
Okay. Well, can we get a little further to the right?
36.1.
That's the outside. There's a weather station we have.
Yeah, Mount Wilson has its own weather station. Whew. I am impressed with how clear it is, though.
After right getting to 9 o'clock and later, the air stabilizes out
Yeah.
from all the wind in the very beginning of the evening.
Yeah.
I think it's good. Okay, so we're there.
Are we going to move over?
I'm going to put up the exposure a bit. 10 seconds. See
Okay.
what that gets us. So, we're looking at a galaxy. And normally we don't look at galaxies with the moon, as bright as it is, but we figured, hey, why not? So, the background is going to be bright, but we can definitely see there's a galaxy there. So, whenever you want, Jenny, you can bring the...
All right. I will go over the view of the attic. And there it is! Yay!
So this is a galaxy that is basically edge on. So you're not going to see spiral arms, you're not going to see that kind of structure. What we're looking at here is the disk of the galaxy, and you're going to see dark bits inside. Oh, right, we've got to turn the red lights on. Hopefully that will reduce the background a bit. Yes, very good.
Now you can stack. Maybe, I don't know.
No, I don't think we can.
There's no stars
There's
for
no
stacking.
stars.
I think I should be
It'd
right.
just be skewed
Whoops.
everywhere. Well, you might be able to stack with your
just-
wide
we
field
are
of view. Oh, with your wild field of view.
Okay, let's just reset itself.
Oh, that looks good, Chris.
Okay, so we have dust lanes in the galaxy, just like the Milky Way does. So this is almost like looking at the Milky Way in the night sky for any of you who have actually seen the Milky Way in a dark sky. This galaxy is also what we call a starburst galaxy, and that means that it is producing stars at an incredibly large rate. So our Milky Way galaxy is what we call a star-forming galaxy, which means it's ongoing, it's making new stars. We saw them before. Those 4 stars in the trapezium, those are relatively brand new stars. So our galaxy is still producing these stars. But this galaxy, M82, is producing them so fast that it is actually it's almost ripping itself apart. All this extra energy from these stars that's being born, and also the stars dying and going supernova, it produces a galactic wind. And you can't see it in this kind of image because we don't have the right kinds of wavelengths here. But it is truly amazing. If we find, maybe we can find one on the web somewhere where we can show them the galactic winds coming out of it. I don't know if we have a picture of that.
I don't think so.
Okay. And you're probably also seeing it's quite red. And this probably is most likely due to, even though we are seeing the starlight coming through, it is going through what we call interstellar dust. And those dark lanes, oh, hey, the seeing just improved really dramatically there for a second. So those dark lanes in the galaxy is not missing light. There's not missing stars. Sorry, it is missing light, but it's not missing stars. It's not like there aren't any stars there. It's the light is going through this material that absorbs the visible light. And not only does it absorb, it also makes it redder. And this is exactly the same thing happens when the sun sets, or for those of you in Southern California, when we had those fires, you remember that the sky would get very red, the sunlight would get very red. That's basically what's going on here.
So Reggie is asking, isn't this where we had a supernova a few years ago?
Yes, 2012J. So that was in the year 2012. And we were down at Caltech, and we were actually looking at this galaxy through a small telescope, and you could see a star. And it was right around, oh wait, I gotta do the mouse over here. It was somewhere, it was on one end. So it was either in here, or it was over
They
here.
had a 14-inch on the roof, didn't they?
Yeah, I think so.
I saw, I looked through that too.
Yeah, so a whole bunch of us were looking at this, and we studied it a lot, because when a supernova goes when it's this close to us, it can usually give us a lot of really interesting information. And this particular supernova was extensively reddened, as we say, so it wasn't nearly as bright as it should have been. If it had not been in this galaxy behind all that dust, it would have been a lot brighter. But as it was enshrouded in sort of these dust lanes, one of these dust lanes here. And so not only was it fainter than it should have been, it was also very red.
So just like you can't see the sun, for example, on a very, very cloudy day, sometimes you can kind of tell where the sun is, but on a cloudy day, the clouds block a lot of the sunlight. The clouds of dust in this distant galaxy are blocking a lot of the starlight and a lot of the light from the supernova. Dust is exactly the right size, which is about the size of a smoke particle, to preferentially absorb blue light.
Oh, okay.
Or scatter the blue light. And if you remember the color order of a rainbow, we have violet, indigo, blue, green, yellow, orange, and red. So if the violet, indigo, blue colors, like if the shorter wavelength colors, that end of the rainbow, are blocked and absorbed, what we see coming through, or what can make it through, are the kind of the yellows and the oranges and the reds, and together they make it kind of a golden reddish color, and that's what you're seeing here. So this is what we call interstellar reddening, or just reddening, and this is the mechanism behind how we see this very red color. and that's because of the dust. So
So
there
we're
you
gonna
go.
bring, let's bring Richard's refractor view in because we get a nice big field of view. And there's also a nice little surprise. I need to make this bigger. Maybe we can get rid of this.
Woo!
Yeah, that's better.
There we go. Okay, so the whoa.
Lost your stacking.
Did you just lose
Oh,
the stacking?
lost the stacking?
Lost 12 minutes with the data.
Oh, 12 minutes of
You
stacking
have to-
gone.
so
I
you
was about
have
to say,
have
where'd it
this.
go?
I'm sorry, that was
Oh no,
my-
there's one underneath. Wait, wait, what?
Right, that's
Is
there.
it coming back?
That's there.
Okay.
Yeah. Don't
There.
don't kill the stack though.
Don't kill the stack. All right, I'll
Don't
then.
kill the
anyway,
stack.
can you see the two galaxies? Yeah. Okay. So
Oh, yeah, look
this
at
is the
that.
one we're looking at through the 60-inch.
M82,
Over here is
M81,
M81.
and it was the gravitational interaction between the two of them that disrupted a whole bunch of stuff, caused a whole bunch of gravitational collapsing of nebulae, just like the Great Orion Nebula we were looking at earlier. So there's a lot of star formation happening, and star formation kind of triggers more star formation, and it's kind of a snowball effect.
So right now we're at 10 minutes of a stack with this one.
That's beautiful. Can you zoom out a little bit on that?
Sure. Better?
That's pretty. Aw, that's really pretty.
All right. Then we can go.
So we're looking at this galaxy edge on.
Oh, I'll go back. Sorry.
If you are at all familiar with the Milky Way, you will know it is called a disk galaxy. And you can think of it kind of shaped like a fried egg. If you're looking down from the top, it looks circular with a nucleus at the center, kind of the yolk. Presumably your fried egg has a yolk that is, in the center, not kind of blobbed on the side. But if you look at the fried egg kind of from the side, if you get your eye down to table level, it will look very flat because it is flat like a pancake. This is what we're looking at it. We're looking at this galaxy edge on. So if we could move ourselves around and look at it from like a 90-degree view way out there in space, it would look like a disk. But we don't have that opportunity. Even moving anywhere in the solar system, this is outside the galaxy. This is a different galaxy, so it is really far away. We cannot get any other perspective than what we have right now. So for those of you who may be a little fuzzy on kind of size comparisons, we have the Earth and the planets and the sun together make up the solar system. The solar system is just one planetary system among, well, thousands. We know of thousands of planetary systems now in our galaxy. But our planetary system has one star. There are approximately 200 billion stars in the Milky Way, and that's one galaxy. This is M82, a different galaxy with hundreds of millions or hundreds of billions of stars and countless planetary systems of its own. It's really far away. The only perspective we can see of it is this kind of side-on perspective.
Oh boy.
Yeah, it's getting windy.
Well, that's okay because we only got 10 minutes.
We have 10 minutes left. It's getting cold in here.
That's getting
Woo! Cold and windy.
All right, so I put the exposure time further up. Let's see how that looks.
I envy all of you people sitting at home in nice warm rooms watching the YouTube feed. 'Cause it's chilly. That is pretty good,
really
Chris.
good.
That is amazing. I think our seeing is actually getting to the point that it is now okay.
I think it could, well, with all this wind, I think we're probably still.
It wasn't abysmal. It wasn't even poor. It was eh.
It
And
wasn't
now
like
it's.
it wasn't like when our mirror was too warm. That was.
Oh yeah, we were up here a month and a half ago, and the mirror, the telescope mirror, is
gas are up to 32
a
miles.
60-inch in diameter round of thick glass. Yeah, it's super windy in Altadena as well. Yeah. You're not sitting outside on the driveway, Reggie. Or maybe you are, looking through your scope. I've totally lost my train of thought. What was I talking about?
No idea.
It's too cold, I can't think. But, yeah, oh well. Nope,
Maybe
it's totally gone.
see if anyone's got any more questions before
Yeah,
we...
any more questions before
close it up,
we
because we're-
close up for the evening because it is getting really windy here.
might be close to the limit.
I'll give that a minute to go through down the... I don't think Reggie wants us to close up. He's like, no. Either that or he's too cold.
Did you
He's
show him,
outside.
did you show him M81?
Yeah,
We did.
I was gonna give a zoom in. I was gonna zoom in.
Zoom in on M81. That's what we're up to
Need to
next.
find it.
And then take it over to the attic view.
Okay.
So this is the zoomed in view of the disruptor galaxy, shall we call it, M81.
Yeah, it suffers a lot more from the background.
Yeah, it does.
Doesn't have any
But it's
red
not
to make
bad.
it pop.
Yeah.
Try it at 60.
60? Sure. You want? Okay, we're gonna move to the. Yeah, it's a very short
Okay,
skip and a jump.
yeah, too cold for the backyard. It's too cold for the 60-inch. Actually, it's not. But we are all sitting here rubbing our hands.
Well,
And I'll
our
huddle up.
CCD is having no trouble staying cold, which is good.
Usually we have to extra cool our CCD so it doesn't get the noise of
I think it's the.
electronic noise. But it's quite cool this evening. Shall we go and try with the attic?
Tom is moving to M80.
Ah, Tom is moving to M81 on
I'll move this
the...
Ooh, it's getting windy.
Wow, I don't know if you guys can hear the wind out there in YouTube land,
Yeah, I know they have to go in there.
but it is...
Can I shut this down?
Sure.
Yep, so Richard is closing up the off-site dome with the...
His monitor fell over.
Oh!
I had
Oh.
to go in there and,
Oh dear. Okay, so to show you, or to explain just how windy it is here, Richard has the 5-inch refractor not in this big dome, but in a smaller dome. Do you want to
Bring it on over and show
bring it on over and show everybody? Okay, so this is another dome on.
there's a monitor missing.
There's usually a monitor over there, and it blew off.
It went over the edge.
Did it break?
I don't know. I don't think so. It's rather lightweight, but
Okay, fingers crossed.
yeah,
You know, this is the
it's not my-
dangers of
it's not my gaming
observing.
monitor, so
You're not your gaming monitor.
Show up there?
we had a fox.
Fox, okay.
Okay, so I want to.
You know, the question down the pipeline and here from YouTube is wonderful observation. Is there any researching opportunities to participate for community college students? Funny you should mention that because
There might be somebody here with an answer.
there may be. I am professor of astronomy and physics at Glendale Community College, and my astronomy colleagues and I have been.
Hey, that's not bad.
We are renovating our observing pad at the college, and we are going to be buying an automated dome that we can use remotely with a 14-inch research telescope. But in conjunction with that, we are in talks to open up a small research program here on Mount Wilson. And so this, I'm not sure which community college you are associated with, and I don't know how quickly Mount Wilson and Glendale Community College will be able to get a research program up and running. I think everything is in place. We just need to come up with project plans and figure out how community college students can get credit for this. But nothing is happening until everything opens up again. I mean, the pandemic has... The pandemic is what it is. I would say that it has been detrimental to many people's education, but it has also really opened up opportunities that we never would have pursued. I came up here for the first time in November when we were thinking about doing remote observing for my astronomy lab class at GCC, and it was such a resounding success that we thought perhaps we could do this on a regular basis as an outreach program. And so we've started that. I think probably the big success was Chris and I were up here with a whole bunch of other astronomers for the December conjunction of Jupiter and Saturn. And that was watched by upwards of about 15,000 people the night of the conjunction. By the next morning, my colleagues are emailing me saying, hey, Jenny, there's 200,000 people watch the YouTube feed. So there is certainly an appetite for this type of remote observing. So I'm hoping to be able to continue that in some capacity, even once the pandemic is over. I understand Tuesday nights at Mount Wilson are not heavily booked for actual observing with eyeball to eyepiece, so to speak. So we may be up once a month post-pandemic, but I'm also hoping to have a research program up and running. And I am not adverse to working with other community colleges, including PCC. I am a Pasadena resident myself, and Dr. Hartman and I have spoken in the past, or communicated in the past. I've never actually met Dr. Hartman face to face, but this is something that perhaps we can collaborate on. Because as far as I'm concerned, the more the merrier. If this is an opportunity for more individuals to really dig into the subject matter of astronomy, I say that is just all for the better. So there's nothing super, there's nothing written in stone. We're still working out details, and right now there's no timeline for this because who knows when we are going to open up. I don't know what you're doing at PCC, but Glendale Community College has already said they will be fully remote for the fall 2021 semester, which broke all the faculty's hearts because we desperately want to be in the classroom and actually see our students again. And I'm sure there's a number of students who aren't too pleased. But you know what? Stay tuned. Maybe if you come back in 2 weeks when we have another remote observing session, another virtual star party, we may have some answers for you. I will also, in the meantime, get in touch with Dr. Hartman and see if he's interested in some sort of collaborative community college endeavor. So there we go. Anyway, I think that is it for our evening tonight. That's M81. I thought we said that at the beginning. So this, what you're looking at right now with a telescope view of the attic camera is M81, that companion galaxy to M82, the one that caused all the disruption. And it's really pretty and also looks reddish.
Sorry?
Also looks reddish. Is this also a star-forming galaxy?
It is a star-forming galaxy, not as star-forming, but we're looking at the core of this, and this is probably an older stellar population, so they're redder stars.
Yeah. Older, cooler, redder. Yep. And there you go. Anyway, thank you very much for joining us this evening. From all of us up here, getting quite frosty on Mount Wilson, to all of you down there, I wish you clear skies and happy viewing. Good night.
Good.